A common question that's asked when we're trying to estimate something about the population is how large does the sample size need to be? And one of the fascinating answers to this is that it doesn't matter how big the population is. What matters is how wide or how much error are you willing to accept? So a number of years ago, we did a survey that required us to talk to people in Washington County about, their political persuasions, who they were going to vote for, whether they were Republican, Democrat, or other. And the population in Washington County has about 65,000 registered voters, but the the error that we were seeking is to know the population proportion within 3%. So we needed a plus or minus 3% margin of error. So we needed to calculate how big does our sample size need to be. Well, to do that, if we know what our margin of error is and we know what the confidence interval needs to be, we can estimate how large our sample needs to be in order to get that error. And it's really just reversing the equation that we calculated previously for our error term. So let's say that we're conducting a survey to estimate the population mean. Many times the question comes up, how large does the sample size need to be? Well, it's important because samples are costly. Each observation takes time, it takes money, it takes resources. We know that there's a relationship that the smaller the error, the larger the sample, but at some point each additional sample becomes less beneficial. So in the previous problem, we found that if with 36 people in our focus group, with the sample population or the sample size is 36, that the point estimate is 28.6 plus or minus 78 cents. What if we wanted that to be smaller? What if we only wanted a 50% margin of error? We wanted to keep our confidence interval at 95%. Well, we can calculate that by putting in into our equation, and we can see that this equation here for our error term can be manipulated algebraically such that our sample size, n, is equal to our z-score times the standard deviation squared divided by our error squared. So if we assume a z-score of 1.96, standard deviation from the population was 2.4, and we only wanted a 50-cent error, we find that we need 88.5, but we know we can't sample half a person, so we have to round that up. So we need 89 people in our focus group. Now the same idea applies if we want to estimate the population. The only real big difference here is that we're going to be inputting the standard error of the proportion. So manipulating this equation, we find that n equals the z-score squared times sample proportion times 1 minus the sample proportion divided by the error. Now, we haven't measured the sample yet. How do we find the sample proportion? Well, we have to estimate it. So if we don't know what the sample proportion is beforehand, we would use approximately 0.5. If we know that it's going to be significantly different than 0.5, for example, if we wanted to know what proportion of the population are Democrats, well, in this area of the country, that proportion is very small, so we might only use a p of 10 or 10%. So we run this through an example assuming a sample proportion of 0.5. Oh, I'm sorry. In this example, we have a mail order company problem that's revisited. So 8% were returning customers. We had an expected value of 9%, but we wanted to know within 1% overall, what is the maximum, or what is the confidence interval, or the sample size for our confidence interval. So plugging these values in, our z-score is 1.96, our sample proportion is 8%, 1 minus the sample proportion is 0.92, and then we divide by our error. So our error is 0.05, or half of 1% squared. Wow. We would need over 11,300 observations. That would increase our sample size from our previous 1,000 by over 10 times. Well, we might want to revisit our error. We know that to improve the accuracy, we need to improve the sample size, but maybe that accuracy is not achievable, and we would want to say back that off to a 1% margin of error.